Okay, so the next part of this digital to analog converter presentation, we'll talk about some performance specifications and the common applications. I'm taking this from, as you can see, this is a set of slides that were presented by Mark Hunkele. Okay, so here are some of the performance specifications that we'll talk about. The resolution, reference voltages, settling time, linearity, speed, and errors. So let's first talk about the resolution. It says here resolution is the amount of variance in output voltage for every change of the least significant bit in the digital input. So basically what that's saying, if you know, how much voltage does one bit change? Like if you had a 4-bit number, what's the voltage change between 0000 and 0001? Now you have to know the reference voltage before you can do that, but once you know that and the number of bits, then you can get whatever that resolution is. And you see there, it's the reference voltage divided by 2 to the n, where n is the number of bits that you have, and then that will tell you what the least significant bit resolution will be. And obviously you can see the relation to how this goes with the analog to digital converters when we talked about that. Typically, if we want a higher resolution, that means we want finer detail and the ability to have smaller voltage variations. A common DAC, as it says here, is 8 to 12 bit, and you can see that that will allow up to 2 to the 12th different voltage levels. In any case, when we start talking about resolution, we have a couple other things that we need to look at. This is just sort of the idea behind what happens with resolution. What if we just have a sinusoid? So what this is trying to say here is we have a sinusoid, and we're trying to represent that in terms of a digital number. And if we just have one bit, we only have the ability to say that we can represent it as 0 and 1. So we don't have enough variations on that digital input to give us the output voltage that looks even remotely like that input voltage. On the other hand, if we have better resolution, so a 3-bit number gives us 8 variations, and so you can see, okay, while this sinusoid may again be the dashed line here, if we break that up into 8 different levels that are equally spaced apart, you can see that this black line here, okay, it still doesn't look exactly like a sinusoid. And so this is the desired analog signal that we want, but it's a whole lot closer than this representation right there. So, and obviously if we had some voltage like that and we had some capacitance there to allow this slow decay, we can get a possibly even more accurate output signal in the end. But the resolution is important because the number of levels obviously allows you to have a better representation of whatever signal you're trying to mimic. Okay, so the reference voltage is another performance specification, and really this is one we already talked about. It says, okay, we can have a specific voltage that we're going to use to assign that output voltage to be a certain value. And it shows really here 2 types: the non-multiplier type, which is internal, fixed, and defined by the manufacturer, or something that we could actually put an external reference voltage to for a multiplier type, and then Obviously that's a little bit more useful if you have something that you're trying to use in multiple places. So anyways, I wanted to sort of give an example of the two types. And, you can see the non-multiplier type here. It's basically saying the reference voltage is C. This is more this standard type that we're looking at here. And you can see that we basically have, for a 2-bit DAC, we have this sort of four separate levels that we're going to use to approximate this sinusoid. Now, on the other hand, if we have this multiplier, our reference could be this sinusoid, and you can see that while similar, we get different. Obviously, the sinusoid will give something different where you're looking at the how that value is incorporated into the output voltage, because what you can see here is still that this A and the coefficient of the sinusoid is reflected there, and you're changing the magnitude of that sinusoid to get the overall version of what the output looks like. But that's not the typical one that we are looking at here in our lab, but it is a possibility. Settling time is another performance spec, and basically that's sort of like the opposite but similar to our analog to digital converter, where you had to sample in the analog value and you had to wait until it charged that capacitor up, and then you could convert it, and you had to wait that conversion time, that settling time for that to take place before you could do the conversion. Same thing here. The time required for the input voltage to settle to the expected output voltage within, this variation of just the voltage level of the resolution that we talked about. And it says here, any change in the input state will not be reflected in the output state immediately. There is a time lag between the two events. So again, you just have to wait that time before you can settle on the desired output analog value. So this is just sort of trying to show you what happens if you have the analog output voltage. So you have some digital value that's being converted to an analog value by your DAC, and it's going along in time. And what this is trying to show you is, okay, if you want to make sure the value is between plus the resolution of your converter or minus the resolution of your converter, you have to wait the length of time. Once you get past this point in time, notice that it's settling down and it never goes above the resolution change of the for the expected output voltage. So the settling time it shows is this length of time here. And so again, what that means is if you're doing this, you can't really count that your output voltage is going to be exactly right and to what you expect it to be with your digital to analog conversion until that settling time has occurred. Okay, so now we're going to talk a little bit about the linearity performance spec, and that's going to be something a little bit different and not something we'll talk about too terribly much, but basically it's the difference between the desired analog output and the actual output that we get for the full range of expected values. I think it's really easier to sort of show this through graphs rather than just talking about it. But you can see here that it says you would hope that you produce a linear relationship between the digital input and the analog output, but you always don't get that scenario. So here it's showing perfect agreement with linearity, and basically you see this straight line going through this, and it's saying, okay, each particular binary level that you have, so this level, this level, this level, this level, this level, has this same separation to it. And so if you don't have that particular case, then you can have some particular problem, and you can see here's this misalignment. Now this of course would be terrible, but this is showing that, you know, the linear output should be there, but what happens if you get that this, you know, value, which would be the first step up from the lowest, is it's up here and then it goes back down for the next one. Obviously that would be a horribly misaligned conversion, and so you really hope that you don't have anything quite as bad as this, but you do have to worry about it. And we'll talk a little bit about that again. Speed is another performance spec that's sort of related to this, the settling time. It basically says here, this is the rate of conversion of a single digital input to get its analog equivalent. And notice I say here, it depends on the settling time of the converter, and also the clock speed of the input signal as well. Here is some of the nonlinear errors that you might get with the graphs that I was sort of talking about, as well as some other errors that you might get from gain offset and non-monotonicity. Here's this differential linearity, and what they're trying to showcase here is, notice that in this one bit right here, it's showing, it's sort of hard to read on this slide, it says 2 VLSB right here, but the problem is the difference between this level and this level should be more like right here. It should be going right here and then going up to this one. So there can be a problem with the step size, and it can be just from one voltage step to the next, and it shows here ideally the differential nonlinearity should be just the resolution of the least significant bit. So the difference between each jump here should always be VLSB. And so this is telling us, oh, okay, here's what can happen if it's not that case and we have the nonlinearity of one of them having two. And typically you would sort of guess that your error would be more like something like this. So not only is this bit messed up, this bit is also messed up. This bit may be back to pretty much normal, but notice once we've gotten off and we're above these levels, we're sort of consistently above these levels until we, not maybe I shouldn't say consistently, but we're above those levels until we come back down and probably approach the ideal from that. Here's the integral nonlinearity. Again, this is basically saying this is the deviation of the actual DAC output from the ideal, and you would hope that it's 0. But this is just showing, again, ideally we expect to be along that line, and it's not doing that same output, and we have this nonlinearity of 1 VLSB. And so here it's trying to show that right there. It's a little hard to see in this slide, but it's off. So that's again a problem. Now the gain error is, well, what happens if overall, it looks like it's doing the same distance between consecutive levels like you expect, but it's not really following that pathway along here that you expect. Now you can't see this one right here, but here is the high gain one saying, okay, again, between each step it may be the same, but it's just too high. This one, it's too low. So you basically having a variation from this desired slope that you want right here for the DAC. The offset error is something, again, that's sort of similar. The offset error, again, what happens if we have our normal slope and then the DAC operates from that, and instead we have some offset voltage, so not just the gain. And remember, we talked about the offset and gain when we did the analog to digital converter, so this is the same thing but in sort of the opposite relation. So instead of doing this, we can have a negative offset voltage, so everything would look okay, but it's offset in the negative fashion, or it's offset in the positive fashion. So we're just basically saying, okay, we've taken a number that, typically we would think it's between 0 and Vref, but now it may be between V1 to Vref plus V1, and that V1 could be a positive or a negative value to allow this sort of offset. Here, this non-monotonic error talks a little bit about it, and you can see in this graph it says a decrease in output voltage with an increase in the digital input. That's sort of the case that I talked about in the very beginning, saying that it was really messed up. You do not expect to go something like from 001 to 010, and then that raises the voltage to some level, and then when you go to 011, you would not expect that voltage to be less than the voltage for 010, but it could be if you have this non-monotonic error. Obviously, that's in a way sort of the worst case scenario from the errors that we have seen. So anyways, obviously there's lots of uses for these digital to analog converters. We have main use in digital audio. There's a whole special section in your book about digital audio. We're really not going to talk about that too much, but it's a worthwhile application for sure. We also can use this in terms of using the digital analog converter to make a function generator. It can be used for oscilloscopes. Also, it can be used for motor controllers. And basically the idea is, we're trying to do something with the digital analog converter whenever we have some continuous analog signal that we want, and we can take our digital input, go through the DAC, and however many bits in that DAC we have, that can give us different resolutions. And here this shows the piecewise continuous output. We can run that through a low-pass filter. That's sort of like the capacitance that I talked about, and it can change this piecewise continuous output into something that looks more like a standard analog output. Another application that was talked about over there was just circuit components, and there are things like uses of these things, these DACs for something else. We can have a digital input and an external reference voltage as control for a voltage controlled amplifier. You might see that as a VCA referenced. You can have a digitally operated attenuator, so you have a reference voltage as input, and you have this attenuator, and that will operate sort of like a potentiometer, but digitally. You can also have a programmable filter with using a digital to analog converter. Okay, so the next section will be talking about the onboard DAC of our particular STM-L32 boards. So the previous two sections were just talking about hardware and also errors that you might get, but this one is now going to start talking about our specific board.